Okay, hi everyone. We have another meeting of the Dynamics and Number Theory seminar, and Felipe will tell us what it's all about today.
Happy to. Welcome everybody. Today's speaker is Zachary Selk from Queen's University. He will be speaking on stochastic calculus for the theta process. Zachary, go ahead.
All right, so I'd like to first thank the organizers for inviting me. And so I'll be talking about stochastic calculus for the theta process. And the start off will be with quadratic Weyl sums. So we take these quadratic sums where alpha and beta are not both rational. So one of them can be rational as long as the other one is not. And it was originally studied by Hardy and Littlewood, very classical stuff. I won't go through the history too much of the Weyl sums. But I want to mention a little bit that you can think of Weyl sums as a approximation to a Jacobi theta function, but on the real axis. So the Jacobi theta function is defined on the upper half plane, and where we sum over all integers. However, when y is positive, we have a little bit of decay, so the sum makes sense. And in the Sn for the Weyl sum, we don't have any decay, so we have to cut off at finite n. And one thing that that Jens Markov and Francesco Celerossi and several others have been doing has been realizing these sums as weighted exponential sums. So you can view both of the Jacobi theta function and this Weyl sum as an exponential sum with some kind of decay. So if f is a cutoff, just a sharp cutoff, that only tells us that we sum over a finite range, or we can have f being a decay that lets us sum over the entire range, but ensures that the sum converges. And there's a whole framework of this. So in order to study these sums, what we want is we want a Lie group, and we want an automorphic function depending on some choice of f that will yield either the Weyl sum, the Jacobi theta function, or other types of sums here. And I'm going through this as it's mostly this has been in the literature for a little bit, but the group that works for this is this Jacobi group. So we take SL2R with with its universal cover. We take semi-direct the Heisenberg group, and this is the group that we're interested in. We define an automorphic function on that, and then the point is for various choices of f, various choices of parameters in the group, we can get these different sums. And by Iwasawa decomposition, you can apply Iwasawa to SL2R. You can apply, well, the Heisenberg group here you can think of as kind of just as R3. So we have the upper half plane, we have this phi coming from the Iwasawa decomposition, and then these three other variables coming from the Heisenberg group.
Excuse me, so maybe can you explain how this semi-direct product works? I mean, so one group is acting as automorphisms of another group.
That's right. So the SL2R is acting automorphic as so it's the SL2R acting by
How does it act?
So actually, Francesco, could you say something here about that?
Yeah, so in the Heisenberg group, there is an R2 embedded in it. So you can see the C1, C2. So the SL2R action on R2 is just by linear transformation. And then you can lift that action to the whole Heisenberg group. Here, Zach wrote it basically as a set as R3, but you can identify it with the upper triangular matrices, the 3x3 upper triangular matrices. And then you can somehow extend the usual linear action from just R2 to this three-dimensional Lie group using like the standard syntactic form in the third variable. There you have to just write down now the formula. But if you think of it as an action on R2, it's just a usual linear action, which is kind of lifted to this three-dimensional group.
But it's SL2R, and then you have universal cover. So for this, you need the central direction.
Yeah, you can lift it to the basically the zeta variable. When you act on by a phi, which is a real number rather than just an angle between 0 and pi, you can when you write down the formula still makes sense, and then you can just say, well, let's take phi to be a real number.
Okay. All right. Thank you. Thanks for offering help here.
So I just wanted to mention the automorphic function we can define for, first we define it for smooth f, and we can give this parameterization coming from the decomposition. The f sub phi here is a Fourier-like transform where f sub 0 is just the identity operator. And, you know, again, for this particular choice of parameters, we can recover these theta sums, or these you know, these Weyl sums. Okay. And in general, it's generically only well-defined if f is a smooth function. You can additionally define as if f is an L2 as an element of L2, so defined almost everywhere. You can define it through representations as well, and it is also, you know, it's invariant under left multiplication by 5 elements of G. So there's a particular subgroup. It's not super important what the subgroup is, but the important thing is that the quotient is going to be finite volume.
Wait, so what do you mean by 5 elements? Some specific elements? Or
Yeah, there's 5 specific elements. That's right.
Any 5 elements?
No, there's 5 specific elements. I didn't write what they were, but there's just 5 specific elements. It's not super important what they are. And then those 5 specific elements, you take the lattice generated by that, and then this theta is invariant under that lattice. It's not super important what the lattice is. The important point is that it'll have the quotient will have finite volume.
Okay.
So it's non-compact, but finite volume. And for smooth f, we have that it's well defined on there because the invariance. And then for non-smooth f, things might not be well defined everywhere, but almost everywhere. And as an element of L2, this theta f is well defined. Okay. And then it takes us to the theta process, which was, you know, constructed by Celerossi and Jens Markov. So the point is, if you take 2 numbers that are not both rational, alpha and beta, you take any probability measure on R that is absolutely continuous with respect to Lebesgue measure, and you draw the x variable with respect to that lambda, and then you take xn to be, you can think of this as you can think of the theta as the Weyl sum as sort of a random walk in the complex plane. And then you can connect it piecewise linearly. And then if you take the same scaling as you would for, say, a random walk converging to a Brownian motion, you can show that this converges weakly on the space of continuous functions to some process. It's called the theta process. And you can think of this as kind of like a version of Donskoy's theorem, except for these sums, these theta sums. And this was proven by Celerossi and Markov. And I can show a few pictures of at least the approximate ones. So for various choices of x and then n very large 60,000, you can get these different, you know, these different approximations. And one thing you'll notice about these is that there is a lot of, there's these places where there's a lot of swirling, and then there's places with a lot of, you know, where it moves pretty fast, then it goes into another swirl. I believe that these are called curlicues.
Oh, this is cool.
So I believe that these are called curlicues. And one thing that we do later on, and we'll talk about this, is we can use what we're going to construct later, these rough paths, these Levy areas, that will let us actually study some of these curlicues a little bit more.
So what's the meaning of colors?
It's just where it starts and where it ends. So I think it starts at blue and then ends at red.
The other way
Or-
around, starts at
Or the other way
red,
around,
we
starts
start
at red
at
and then goes
0.
to blue. It's just for the time.
Okay.
And we can explicitly describe this theta process. So what we do is we first draw uniformly according to Haar measure on G mod gamma, point G. We apply the geodesic flow on this up to time 2 log t. We map under this theta function and scale by square root of t. And this is the limiting process that we get. And again, there's a few things that are difficult here, but one thing that Markov and Celerossi had to work very hard was the smoothing and unsmoothing of the chi. So this is only defined almost everywhere for almost everywhere G, but that's good enough for defining this process. And then you have to also check that's defined along the entire geodesic flow for almost every G. And this is the theta process. And then where the work that I've done with Francesco recently has been developing the calculus for this, developing stochastic calculus for this process. So I want to mention a few properties. We don't have to go through all of these, but it has mean zero. It has a particular covariance. The really crucial parts of this are going to be the third and fourth that are very different from Brownian motion that you would get from a normal random walk. And so X has dependent, but they're uncorrelated increments, and it only has 6 minus epsilon moments, where if you have a standard Brownian motion, it has independent increments and infinitely many moments. But other than that, this looks very similar to Brownian motion, very similar to other types of processes. So one crucial point that I wanted to mention here, because we're going to be talking about the stochastic calculus of this, is that X is in particular not differentiable, which is one of the biggest hurdles to doing calculus with it. And we were able to show the Holder continuity and the p variation. So in the previous paper, Francesco and Markov showed that with probability 1, X is alpha Holder for all alpha less than a half. Recently, we were able to show the converse, that is not alpha Holder for all alpha greater than a half. We're able to show the quadratic variation of this, which I'll define in a little bit later, which is notably different than the 2 variation of this process. But the quadratic variation of X is t. And one question you might want to know would be, how do we show other types of properties for this? And for that, we need stochastic calculus. So stochastic calculus has been extremely successful for studying things like Brownian motion, which again comes from the same kind of Donsker scaling limit, and has been extraordinarily successful for proving things like conformal invariance, proving things like changes of measure with Gersonov and all kinds of properties like that. So if we're interested in those kinds of properties, we need to develop a theory of calculus for X, and that is our main contribution. So let me just mention kind of what the goal of stochastic calculus is. So the goal is basically, if we have a smooth function of a stochastic process, here I'm just writing as a general Z, we want to be able to define derivatives, right? We want to be able to take derivatives of functions of the process, right? But in general, it's very uncommon to find interesting stochastic processes that are differentiable. So Brownian motion is an example of something that's not differentiable. There's more general processes, fractional Brownian motion. These aren't super crucial for the point. Crucially, X, the theta process, is not differentiable, and that's very important. So it's not, we have to find some way of constructing a calculus for this process that isn't the standard differentiation. And I mentioned, one thing you might ask is, okay, you can take a derivative. What if Z, you just take the distributional derivative? But the issue there would be the product of f of z times z prime, because products of distributions are in general not well defined. There's sometimes where you can define the products. So, but I don't want to get into this right now, but in particular for the theta process, you can't define these products. Okay. So one thing that you can do is you can go from, okay, we can't differentiate, but maybe we can at least integrate. And we can interpret derivatives kind of inverse through integration. And that is what stochastic calculus is. Stochastic calculus studies how do we define integration against a process, right? How do we define something that is integration against something that is not differentiable, generally not of bounded variation, and very, you should expect it to be very ugly, right? So I'm going to go through 3 attempts at stochastic calculus. The first is going to be a purely analytic, so that's just defining, a Riemann-Stieltjes sum or going through Young integration. The second is going to be the Ito theory, which was extremely successful for Brownian motion, but we proved that it can't be done for the theta process. And then the third thing is going to be rough paths theory, which actually does work for the theta process. So the rough paths theory is going to be is a very modern theory developed in the 90s. And it really uses both analysis and algebra to make sense of integration theories. So I'm going to go through the first 2, explain why they don't work. And then I'm going to go through the construction for the third one. So the first one is just, okay, we need to define an integral, just the very most basic. All right, can we just define this as a Riemann-Stieltjes integral, right? So can we define this as, we take a sequence of partitions with the mesh size going to 0, we take a Riemann-Stieltjes sum, does this limit exist, right? And there's some results on this, a very classical result from Young in 1936, which tells you, which gives an example of when this might exist. And it comes down to p variation. So if we have 2 functions, and this 1936, this is just about functions, right? We're not using any probability, any randomness here. We're just taking a function f and a function g, whose p variation and q variation satisfy this kind of, Holder bound-ish, where it's like 1 over p plus 1 over q is greater than 1. Then Young shows that the Riemann-Stieltjes integral of f against g exists. However, we showed recently that for the theta process, x has almost surely infinite p variation for all p less than 2. So we can't even integrate x of s, dx of s using this kind of Young theory. We didn't show that the Riemann-Stieltjes integral doesn't exist, but it's very, it's we have no reason to think that it does exist. And in general, if we have f of x for a more general smooth f, we'd have to kind of redo all of this by hand. So the Young theory doesn't quite work because x is not regular enough. X doesn't have enough, doesn't have enough variation to make this exist. Okay, so the pure analytic stuff doesn't work. So we can go to Ito, which was extremely successful for Brownian motion, and Brownian motion and the theta process are very similar processes. They both come from some kind of scaling limit. They both have the same Holder regularity, same p variation, even the same covariance and things like this, right? So you might expect something like the Ito calculus works. And the way it works is basically by, okay, we might not be able to define the integral along every path, but if we kind of weaken that to a limit in probability or a limit in L2 or something like that, where we're kind of averaging over the paths, Brownian motion on average behaves very nicely. So we might be able to do something like that for the theta process. And crucially, like I said, it uses the martingale property of Brownian motion. And basically what the martingale property tells you is that if you look into the future, given all of the information up to where you are now, you expect to stay where you are. So like on average, the increments are going to be 0, right? You don't go up, you don't go down. So there's a lot of cancellation, at least when we're averaging over paths, right? And this is really what makes the Ito calculus work, is that you can average over these paths using this martingale property. And then this will let us, show that these Riemann-Stieltjes sums exist in a weaker sense, right? And let me mention a little bit about the quadratic variation, which is a crucial point of the Ito calculus and of Brownian motion. So if you have a real value stochastic process Z, this limit in probability where we take a sequence of partitions with mesh size going to 0 of the second variational sum, this limit in probability is what is called the quadratic variation. And crucially, one thing I want to mention is I define the 2 variation or the P variation as the supremum over all partitions. The quadratic variation is not the same thing as the 2 variation. It's a difference between taking a limit of partitions whose mesh size is going to 0 or taking a supremum over all partitions, right? And one really crucial thing about the quadratic variation is that we have this Lebesgue characterization of Brownian motion. So if we have a continuous martingale with mean 0 and quadratic variation t, then we're Brownian motion. We are Brownian. However, we had showed that the quadratic variation for the theta process is t, right? And what that means is, so by that I mean like each component is t over 2. And what that means is if x was a martingale, then it would be Brownian motion, but we know from properties 3 and 4 earlier that it has heavy tails, that has dependent increments, that is actually, not Brownian motion. So it is not a martingale using the Lebesgue characterization. And then there's this other theorem here, Bigteller-Delecree, which lets you know, which tells you how far can we push Ito calculus. And basically the point is it's for semi-martingales. It's not super crucial for the purposes of this talk, what a semi-martingale is, but it's a sum of a local martingale and a finite variation process. And we prove that the theta process X is not a semi-martingale. And it's a very similar idea of the Lebesgue characterization. It takes more work because it requires, that you can't decompose it into this sum. But basically, being a semi-martingale is very rigid. And again, the quadratic variation being t, it tells you a lot about the process. And if X was a semi-martingale, we show that it would be a Brownian motion. So even without the Lebesgue characterization, it's kind of a little bit more generalization. So the Ito calculus doesn't work for this theta process because X is not a semi-martingale. So
excuse me, can you explain this first theorem of Bigteller-Delecree? What is the statement actually? Ito calculus works only for semi-martingale. If something is not a semi-martingale, then what doesn't work?
So basically what you have to do, the way you define the Ito integral is you define it first through like simple adapted processes. And basically what Bigteller-Delecree tells you is that if you take the set of all simple adapted processes that are bounded in suit norm, then the Ito integral that you would define for those is not bounded in probability if you're not a semi-martingale. It would take a while to go through the full statement of the Bigteller-Delecree, but the crucial point here is that all the Ito theory is sort of predicated on being a semi-martingale and approximating by these simple adapted functions, and you're not able to do that here. So you're not really able to develop the full theory of Ito calculus. It would take a long time to go through the full statement and prove for things of that for this theorem. But the crucial point is X is not a semi-martingale, and we're not able to do Ito calculus with it.
Okay, but now I'm confused. Your theorem says that X is not a semi-martingale, and you prove it by saying that it's not a Brownian motion, or vice versa. You say that it's not a Brownian motion because it's not a semi-martingale.
Oh no, it's not a Brownian motion because of the properties of moments. So X has 6 minus epsilon moments for every epsilon. Brownian motion has infinitely many moments.
Okay.
So it's just the fact that there's any difference at all between X and Brownian motion. It's not. So if X was a semi-martingale and it had certain properties, we show that it would be a Brownian motion. So if it has the quadratic variation of t, if it has the covariance, and it's a semi-martingale, then you can prove that X is Brownian. So it's a proof by contradiction. Assuming it's a semi-martingale, then we show it's Brownian, but it's not Brownian, so it's not a semi-martingale.
Okay.
Sure. And then crucially, the thing that does work is going to be rough paths theory. So the rest of the talk is going to be dedicated to constructing a rough path above the theta process. And essentially, rough paths theory, it takes a very axiomatic or algebraic approach to integration theory. So basically, the question is, we want to go back to the drawing board of, all right, what do we want our integration theory to satisfy, right? What do we want this to actually do? So we want really three things. First of all, we want to be able to integrate 1 dz and get z of t minus z of s. We want to be able to add the endpoints. So the integral from s to u plus the integral from u to t is the integral from s to t. And of course, we want to have linearity of the integral. And this was introduced in the late 90s. And since then, it's seen a lot of growth. It led to a Fields Medal in 2014. It's been applied in, I have some colleagues applying rough paths theory in medicine. I know some people, in control theory and all sorts of things. So it's been a very successful theory recently. And it's sort of, and the point is, it uses the algebra. So we're not able to just do analysis alone because X is not regular enough. We're not able to use Ito because X doesn't have the kind of cancellation or martingale properties. However, X, we're able to construct a rough path above X. And I'm going to introduce a little bit of what rough path theory is and then relate it back to the sums that we were interested in. So the question is, if we have these three properties of an integration theory, can we reduce defining the integral of f of z dz to something a little bit more manageable? Like, what is the problem? What is the fundamental issue in defining this? So I'm going to go through and give a little heuristic derivation. So we have these three properties that we want. So we want the integral of 1, we want a Chesler relation, we want linearity. And the point is, if we have a signal that is alpha Holder for some alpha greater than a third, the third there doesn't mean anything other than just we might have to expand a little bit more in this final line. And we have f being smooth. So what we can do is we say, okay, if we have an integration theory that satisfies these properties, well, first what we can do is we can take a partition and we can use property 2 to write this integral as a sum of integrals along the partition, right? And then since f is smooth, we can Taylor expand f and then use the Holder regularity to get that the remainder is of order tk plus 1 minus tk to the 2 alpha. Then we can use linearity and we can use the integral of 1 to get the third line. And really the point of rough paths theory is that if you assume these three properties, if you assume these three axioms, then you can reduce defining the integral of f of z dz to this third line here. And if alpha is greater than a third, the third guy will go to 0. And the reason I chose a third, you could go to a fourth, you just have to Taylor expand another degree. And in general, you just have to Taylor expand large enough so that way n alpha is greater than 1, right? And the point is, if you look at this third line, this is a Riemann-Stieltjes sum. The first guy, if you ignore the second and third terms in the sum, this is just a Riemann-Stieltjes sum, right? The second term is a correction term. It's something that guarantees that this limit exists, guarantees that, or that's the hope, and rough paths theory tells us that that's true. The third guy goes to 0, so we don't have to worry about that. So you can think of rough paths theory as a integration theory or a generalization of Riemann-Stieltjes integration, where you add this correction term, and the correction term is exactly the iterated integral of the process. And why it's an iterated integral is that z of r minus z of tk, you can use property 1 to write this, this second term as a double integral of 1, right? And the point here is, in order to define a stochastic calculus above the theta process x, what we have to do is we have to define the iterated integral, the z dz, the integral of z dz. And you can think of this as kind of a reduction of complexity of, rather than having to define this for every single smooth f, all we have to do is define z dz, and then the rest of the stuff follows. Okay. So let me go to here. So the key idea of rough path theory is that we're able to reduce defining f of z dz to defining z dz. And we really want two properties this iterated integral to satisfy. So we want it to satisfy an algebraic property, which will be Chen's relation. And then we want it to satisfy analytic property, which is Holder continuity. Okay. And let me go to a formal definition here of what a rough path is. And I'll pause on this for a little bit and try to explain everything that's going on here. So a rough path, basically, it's something that takes in a pair of times, s comma t, and then it gives you something in this truncated tensor algebra, rd, o plus rd times d. So it gives you a, it gives you a vector and it gives you a matrix, right? And the vector is just the vector part is just the increment of the function. The matrix part is going to be the part that we define or we use to define the iterated integral. And it's a matrix because what we need to do is we need to define the iterated integral of the ith component against the jth component. So the ijth element of rd by d is a definition of the integral of zi dzj. Okay. And we want it to satisfy two main properties. So the first one is just saying that, the property one is just saying that the first element is just the increment of the original process or function we care about. The second thing there is what is called Chen's relation. That's a purely algebraic relation. I'll talk about that a little bit on the next slide about where Chen's relation comes from. And the third guy is an analytic relation. So we need to be alpha holder in the first component and 2 alpha holder in the second component. And this defines a metric, right? And we can put a metric on the space of rough paths, which a rough path is, jointly a signal and an integration theory and a notion of iterated integrals on top of it. So one thing you can think of with a second guy is sort of keeping track of extra area. It's keeping track of extra information in the path. So one classic example people give would be if you have a path that's tracing out a circle in the plane where the radius is going to 0, but the area it's tracing out is a constant 1. So as a path, this converges to the constant path 0. But as a rough path, the first part is 0, but the second part contains the fact that there's extra area. It contains that information. So the second part, when things are very irregular, somehow contains more information and lets you actually define integration later. And the Chen's relation, this part 2 of the definition here, it might seem a little bit esoteric of what that really means, but it just comes from multiplicativity. So let me just give, this is another way that these iterated integrals show up, is if you have a smooth z and you have this differential equation, y prime of t equals y of t, z prime of t, starting at some time s with y of s equals 1. The solution of this is just this exponential of the increment of z. And if you Taylor expand that, you end up getting all of the iterated integrals, right? And all of the iterated integrals is what we call the signature. And all Chen's relation is saying is that we want, under this exponential map, a kind of multiplicativity. And I'm not going to get into this right now, but there really is a legitimate Lie algebra, Lie group, a genuine exponential map in the sense of Lie theory that you can do all of this. And Chen's relation, if you look at the bottom, is if we go from S to U and then from U to T and multiply all of that out in the truncated tensor algebra, Chen's relation is exactly the third guy. The second order from S to U plus the second order from U to T plus the first order O times the second O times the first order is going to be the second order from S to T. If you just move all of the second order to one side then you get exactly the Chen's relation that I wrote there. So the Chen's relation, all it's saying is we're respecting the multiplicativity of this exponential map. And anything that satisfies this, we call a rough path above the signal z. And our primary contribution is we construct that. Yeah, and let me give one more understanding of what this rough path is doing. So if you have a smooth function z, you can look at the difference of iterated integrals zi dzj minus zj dzi. This is called the Lebesgue area. And the reason why this is called the Lebesgue area is by Green-Stokes theorem, this is going to be twice of the area that is swept out by the curve, okay? And we even have this for the theta process. So on the left is an instance of the theta process, and on the right is its Lebesgue area, okay? So one thing that the Lebesgue area actually lets you study is it lets you know when these swirls happen. So when these swirls are happening, you see a lot of oscillation, but not much growth in the magnitude of the Lebesgue area, right? So, and then when you sweep out a larger area, you kind of grow up, you kind of go up in the Lebesgue area. So the Lebesgue area here, this difference of iterated integrals, actually helps you pick out when you're swirling and helps you pick out when you're sweeping out. So the Lebesgue area will actually tell you something about the swirls. Okay. So let me just mention about the existence of a rough path lift and the lack of uniqueness, right? So there's this there's this result from Lyons and Victor in like 2009, which says that if you have a signal that's alpha Höhler between 1/3 and 1/2, I think they might have even done more general than that, then it does have some abstract lift. There is some process, there's some second order process that satisfies the conditions that we said before. And but the problem is it's a very unnatural lift. So they give some abstract results in analysis, basically saying if you can define it on dyadic times, then you can construct it for all times. And you know, they define it on dyadic times inductively in kind of a you know, it's a beautiful result in the sense that it you know, it applies for any signal, but for any given signal that you're interested in, it's not going to be a very convincing construction, right? And in general, you're not going to have a canonical choice of a rough path above a signal. You're always able to construct an infinite family of rough paths above your signal. And the reason is that you're always able to add on an increment of a 2 alpha function. Okay. And the point is, we have to make some choice. We have to make a choice that is reasonable. And one of the best choices we can make would be an approximation. So if we have a rough path with a geometric rough path is going to be a rough path that you can approximate in the metric that we had defined earlier by smooth paths or by piecewise smooth paths. So the point is that if we have a smooth path, we can canonically enhance it with its Riemann-Stieltjes integral, and then we can approximate in the earlier metric any then we can approximate all of these other ones, all of these other rough paths, and the ones that we can approximate are these geometric rough paths. So not only do we want to create some abstract lift, we want to construct a lift that comes from an approximation procedure. And in particular, we want to construct from, you know, the approximation procedure that was given in Celerossi and Marklov's paper of piecewise linear approximations. So let me just mention the integral that I wrote out earlier, this rough integral, does exist, and you can think of it as a Riemann-Stieltjes integral with a correction term. The f prime of z, then the bold z is a correction term for the Riemann-Stieltjes, ensuring that this Riemann sum converges. And you can generalize, so I was defining f of z, you can generalize this much further to solutions of rough differential equations and a bunch of other things. But the point is that at least for f of z, we're able to construct an integral as long as we construct the second order process, which is the iterated integral. Okay. And our main theorem is that we have xn, the approximation. So we have the Weyl sum, and we approximate it piecewise linearly and scale by square root of n. And we enhance that with its canonical Riemann-Stieltjes integrals. Then the laws of that converge weakly on these geometric rough path spaces to a geometric rough path, right? And the really crucial point why this kind of ties back to number theory is it turns out that iterated integration is the same thing as iterated sums, iterated exponential sums. So really the interesting point here is we're able to just study the second order process by studying second order theta sums. And let's go to an expression for xn. So I'm just going to write, because the theta process is complex valued, so it has two parts, the real part and the imaginary part. And we're treating this as kind of an R2 valued process, right? And again, the rough path is this matrix of integrals where we have the real d real, we have the real d imaginary d real, and imaginary d imaginary, right? And we need to construct all four of these in order to construct a rough path above x. The diagonal terms are really easy. So for any rough path, for the diagonal part, this is always trivial. You can always define the diagonal terms just to be 1/2 the increment squared. And this is true just by, or it's not even a definition. This is just an equality here, right? And then this is just by, the U substitution. And then the limit of this guy as n goes to infinity, squaring is a continuous function. So you just take the limit of it. It's not too hard. Really, the issue is going to be the off diagonal term. What is the integral of the real part against the imaginary part, or the imaginary part against the real part? That's really where the work takes place. The diagonal is always the easy case. And for the off diagonal terms, that's we can consider at least at the grid points, at the points k by n. And you can just compute for consecutive grid points just what the Riemann-Stieltjes integral is. So for the Riemann-Stieltjes integral on consecutive endpoints, you just have 1/2n, ak plus 1, bk plus 1, where these are the real and the imaginary parts of the exponential, okay? And there's nothing special about the Weyl sums here. So there's nothing here on this slide that has anything to do with Weyl sums. Any exponential sums we're able to do everything on this slide. So there's been some work done on Kloosterman paths, for example, and any other exponential sum can be decomposed in this way. So really, doing rough paths theory above these kind of processes coming from these exponential sums can be reduced to looking at these higher ordered exponential sums. So I'll do a little bit more. I'll say a little bit more in a second about that. But the Chen's relation that I mentioned earlier. So for consecutive points, we have this 1/2n, ak plus 1, bk plus 1. Then for non-consecutive points, if we take k and k prime, then we end up with a term that's the am bm, where the indices of the a and the b are equal, and then this kind of sum over the simplex, the sum over m less than L, right? And yeah, so that's for non-consecutive points. And then for points that are not on a grid point, the error will always go to, we can show that the error goes to 0 if we're not on a grid point. We just take the closest grid point, and then the distance between that closes, and we don't have to worry about that. And for the first part where am bm, where the indices are equal, we can just apply the double angle identity. So this term just goes to 0 almost surely because it's over normalized. We're dividing by n here. So that part is not too bad. It's really the second part that we have to care about. And, because it's a real part and an imaginary part, we can use a polarization identity of the complex numbers and say that, really studying the iterated integral boils down to studying the sums of ZMZL and ZMZL bar. If we can construct those, or we can study those, then we can study the entire, then we can study the iterated integral. And the ZMZL is pretty easy because, again, that's just going to be a square of the original part of the original sum minus a diagonal term, because we're not including m equals L, and we already showed that the diagonal term goes to 0 almost surely. And the point is, through all of this, it ends up being that we need to study the iterated Weyl sum that's given here, where it's a second order Weyl sum over the indicator of a triangle, right? So it's a sum over all n1 and n2 integers, and we have these triangles that we need to sum over. So, and also the we have n1 minus n2 in here, which we can correspond to different alphas, different betas, but with minuses. So let me go to this guy to a second order theta. And this has been some work that Jens Markloff has done recently with Welsh, has been studying higher ordered theta sums. So rather than just summing over one, we can sum over 2 indices or 3 indices of some function f. And it's exactly defined exactly the same way, except we have, just double copies of everything, right? There's only one zeta there because the two phases, they can add to a single phase out there. So there's only one zeta. That's not a big deal. But one crucial point why this is a different problem than the original one is that the f we have, it's not a product of two functions. That is the main difference here. It's not a product of two functions. In particular, the case of the triangle, the indices are tied together, right? The components are tied together there. So we're not able to actually just use all of the same stuff from the first order, because if we could just split the sum into two, then that would be fine, but we're not able to split it. So the lattice that we mentioned before, this gamma lattice, the second order theta might not be invariant under the product of gamma with itself, because f is not necessarily a product of two functions. And one thing you can do is you can embed G cross G into this larger group SP4, semi-direct second order Heisenberg group, and then exists some larger gamma 2, so that G2 mod gamma 2 has finite volume. And the reason why we have to embed into this larger space has to do with the regularity of f. So for us in the second order process, the f is the indicator of a triangle, which is not smooth. And the point is, when you unsmooth it, the way you have to unsmooth it, it actually starts seeing other parts of this group of G2 if you want to unsmooth it in kind of a dynamical way. So we have to embed into this larger group, and you can kind of think of that as like the second order process is like giving more information, and the second order process here is sort of seeing this larger group, even though it lives on a strictly smaller submanifold there. So this is only
what is this?
Hmm?
Sorry, what is this H of R2? What does it mean?
It's a larger Heisenberg group, so it's like you have R2 cross R2 cross R. So it's basically, you can think of it as R5.
Okay.
Okay. And really, we have the second order theta, which is in G cross G. But for our purposes, everything in the second copy of G is the negative, or not everything, but half of things are the negative of the first, and then half of them are equal in the first copy of the G, right? So really, the second order theta still is supported on this 6-dimensional submanifold of this G2. However, in order to actually do the smoothing and unsmoothing for the sharp triangle, we have to leave that 6-dimensional submanifold, see these other spaces, and then kind of come back in order to do the unsmoothing in a dynamical way. Okay. And let me just mention the ingredients for weak convergence. So it's tightness. So we need some kind of compactness. We need that the measures mu and are tight. And then also we need convergence of finite dimensional distributions, which as a rough path is defined on the simplex rather than the interval. It just means we take collections of pairs of times and then show the weak convergence of those, and then we show the the tightness of the mu n's. So let me just mention a little bit about the tightness. So if you recall, on classical Holder spaces, you have a compact embedding of classical Holder spaces, right? And it carries over to these kind of rough spaces, right? Because these are spaces of alpha Holder in the first, 2 alpha Holder in the second. And basically what we have to do is we take large balls in in these spaces, and these are going to be our compact sets, these compact sets of large measure, right? And this is actually a challenging thing to do, because usually if you're trying to prove tightness for a sequence of stochastic processes, the standard techniques would be this Komarov tightness criterion, where you look at moments. You compute the moments, the expectation of the increment of your process to a power p. However, X, again, only has 6 minus epsilon moments. So Komarov, if you actually try to follow it out, will only get you to alpha less than a fourth. It requires some subtle analysis and a very different thing, a very different proof to get tightness all the way up to 1/2. And it was a very, very crucial point that the lack of moments makes Komarov tightness not very effective. But we show this, so we basically take a large ball in this rough path space for alpha prime, and then that shows tightness in alpha. And then for the finite dimensional distributions, what you can do is you can look at pairs. You look at the theta and the theta 2. So theta over chi of the interval, and then theta over chi of the triangle. And then you show this converges in distribution using some equidistribution of Haar cycles. And then what you do is you write the second component as a composition of theta 1 squared and this theta 2 process, plus some diagonal terms that go to 0. And then Slutsky's theorem and continuous mapping theorem shows the weak convergence. And I'm going to conclude with saying the main theorem we have again is that we have that if you take this theta process xn, you enhance it with its canonical Riemann-Stieltjes integrals, then the laws of this converge weakly on the space of geometric rough paths to a geometric rough path, right? And one thing why this is stronger than the original result by Celerossi and Markov is that, of course, you can just take the projection of the first component, and that's just the signal itself. But it's a little bit stronger. Is this also, even comparing to the first to the paper with Celerossi and Markov, this tells you that the convergence not only takes place on the space of continuous functions, but takes place on the space of Holder continuous functions. So it's a little bit stronger there. Yeah, I think that's about all I have.
Well, why don't we thank Zachary? And are there any questions or comments?
Sorry, can you say again what you just a few slides before you worked with the measures mu n, and you were proving that they form a tight sequence. So what are those measures in the actual theorem?
Mu n's are the laws of xn, comma mathbb xn. So it's the process with its canonical Riemann-Stieltjes integrals. These are both random processes or random functions on the simplex. And then the laws of this on the space of the geometric rough paths. The laws of these we want to show converge.
Mm-hmm.
So you can think of x like the math bold x. Here, the math bold x is a pair of xn, which is the original process, plus math bb xn, which is the iterated integrals of the process. Then the law of this defines a probability measure on the space of geometric rough paths. And then these probability measures converge weakly.
So just the tightness part means that these random walks are not transient. They return to compact sets.
It just means that you have some large compact set that you're supported on, and in particular, this compact sets that we're interested in are holder ones. So we have these so classically the holder spaces compactly embed into each other, right? And then for us, we also have that the rough holder spaces, these C alpha primes and C alpha, where it's the script C, these compactly embed into each other. So if we take a large ball, it's bounded in one, so it's going to be relatively compact in the other one.
Mm-hmm.
So the point is, you don't have escape of any mass to infinity, basically.
Yeah, that's what I'm. So right. So the random walk comes back. This random path come back to some compact set.
In some ways, but it's more about the regularity of it. It's more that these are somehow uniformly alpha holder with high probability.
Yeah,
it's more about the
if I
regularity.
may, if I may add something. So the tightness here doesn't tell you what happens along the trajectory of your path. Doesn't tell you what happens along the as time goes by. Is if you look at this function as a whole, for all time, it lives in a one of these holder spaces, and so it doesn't escape the holder spaces. If you think of tightness done usually with Kolmogorov criterion in terms of bounding moment, you're like controlling that the function doesn't have jumps, so you are not leaving the space of continuous function. In this case, the function is controlled in a way that doesn't leave the space of holder. In that sense, it's tightness. That's some of the intuitive way to think about it, I think.
Okay, thank you.
Other questions? Well, if not, why don't we thank the speaker again? Thank you, Zachary.
Thank you. Thanks for having me.